as you can see, we're not doing so well here. From time to time, you can see the screen. I'm not sure what's happening. Okay, sorry about it. I'm going to try to reset the system, see if that's going to help in any way. We have a sets representative. Chris, do you have any suggestion what I should do here?
I just called a lot.
Okay.
Check the adapter.
I replaced the adapter with my own, but that doesn't seem to be it. Not sure. So this was the adapter here. I changed it to mine, but it's not it. No, I think it's something here because this one is flickering also. That's the one that is connecting this, and this should go. So I think it's this. Oh no, this is nothing actually. No. It's actually unrelated. It's just connected to here.
Almost makes me think we should restart the host, but because we did the system, but not the host.
Yeah, I didn't reset the host. How do I reset the host?
I mean, it's the one we got left. Just in case he calls back.
I don't know how to reset the host. No.
Oh, just your laptop. I mean, maybe log in or out.
Oh, here, you think?
Yeah, but
Okay, I can try that.
that's a pain.
Oh, that's quick, actually.
That's the only thing I can think of. Or log out maybe instead of restart.
And restart, it's quick.
Try them out one more time. You might be able to tell me what to do remotely.
Oh, it's not. I was going to say it's more stable because it was flickering there before.
If it still does it after this, I'm going to run over to the office real quick.
Okay, let's see. I'll try.
So now nothing?
Nothing.
So let me just do one of these now that we've, sometimes I thought about trying a different one. I'm worried that it's this thing.
Well, we can use this.
Yeah, let's try that.
No, it's okay now. Let's wait. Oh. Stable.
Yeah, no one moved.
Okay, thanks. Okay, sorry about it. Hopefully we are back to normal. So, okay. So let me just change the light again. I think since I reset it, it changed the light. I think that's the one we like. Okay. So where are we? So we started talking about online learning, and my goal today is to talk about mostly one learning algorithm, but as we'll see, it's really a family of learning algorithms that will introduce as the Perceptron learning algorithm. Perhaps the most important learning algorithm we'll see this semester, and we'll give also other views of this. So in the course of doing it, I want to address a few issues, and we'll see later how we do this. But first of all, I want to remind us where we were last time. So online learning, sometimes people think about it as a mistake-driven learning algorithm, because in some of the algorithms, we only update our current  when we make mistakes. So last time we asked the question, is it clear that when we learn, we're going to stop making mistakes at some point? We started, just to remind you, last time with playing with multiple learning protocols. We talked about a teaching protocol where the teacher gives you examples, and we try to analyze how many examples you will have to see in order to learn a simple hypothesis. We then talked about interactive learning, where you propose examples and the teacher gives you label. And finally, we got to the perhaps simplest learning protocol, most commonly analyzed, where there's just a collection of examples sampled from some distribution, and we developed under this assumption a learning algorithm for conjunctions. In that case, we saw that we didn't necessarily converge to the hidden hypothesis, but we gave some ideas for why we think what we got to is okay. And then we asked, are we going to stop making mistakes at some point? What was the answer? Are we going to stop making mistakes? Yes, why?
Doesn't matter like what features we choose. Like if we have all features or none features, as we go on, we learn more, and at one point we just get to the point.
Right, but we can actually quantify this. So we said, under the assumption that we have a finite concept class, that is, the number of functions that our learning algorithm even entertains is finite, our learning algorithm will stop making mistakes, because every time we choose one hypothesis from this collection of functions, and we use it as if this is the correct hypothesis. Given an example, we predict on it. If we made no mistake, we're happy. We just stay with this function. Once we made a mistake, we get rid of this function. We take another function that is still valid in this hypothesis space. And that means that every time we make a mistake, we reduce the number of candidates by at least one, which means that if the hypothesis space is finite, we're going to stop making mistakes. So I wrote it here formally. CI is the set of all concepts, all candidate functions that are consistent with what I've seen so far. I choose a function in CI, and I use it to predict on the next example. If I made a mistake, I eliminate it, and therefore CI plus 1 is going to be a strict subset of CI if I made a mistake, which means I'm going down, and I will make no more than size of C minus 1 mistakes. Everyone is okay? I convince you that we will stop making mistakes? Now, last time we ended with the comment that we can do better. And this was my question about the most important algorithm that you've learned in computer science. And we agreed, I think, that what was the most important algorithm, or algorithmic idea, let's say? Binary search. So we can do better if we use binary search. So the idea is going to be, and this is called the halving algorithm, the idea is going to be similar only that in the ith stage of the algorithm, let's assume again that CI is the set of all functions that are still consistent with everything I've seen so far. So given a new example, I need to make a prediction on it. How do I make a prediction? I'm going to consult all the functions that I have so far, that remain so far, and I'm going to ask them, should I say 0 or 1? Some of them are going to say 0, some of them are going to say 1. I'm going to go with the majority. If I made a mistake, so this is me going with the majority, right? The number of those that say 0 is less than the number of those that say 1, so I'm going to say 1. If I made a mistake, I'm going to eliminate all those that misled me, which means I'm eliminating at least half. Right? So you've seen these ideas in other classes before. And therefore, Ci plus 1, the size of Ci plus 1, is less than half the size of Ci, which means in logarithmic number of steps, I'm going to stop making mistakes. I'm going to eliminate all by one functions. Right? Every mistake, I'm eliminating half the functions. If you're not 100% sure about it, start with 32 functions, play this game, and see that in log base 2 of 32, you get to 1. So what does this show? I mean, first of all, this is a theoretical algorithm. In practice, I cannot do this, right? I cannot just consult all the functions in my hypothesis space and ask them, how many of you say 1, how many of you say 0? This is just a theoretical algorithm that says that, in theory, we can do this, but we don't know whether this can be achieved by an efficient algorithm. That's one. The other thing is that here we assume that we have a finite hypothesis space. For example, the space of all conjunctions, right, over, say, 100 variables is finite. Maybe you want to move to an infinite hypothesis space. An example of an infinite hypothesis space would be yeah. Yes, a neural network will be infinite, but even simpler than that. You've already used, and you are using also in your homework 1 now, an infinite hypothesis space. What was the first learning algorithm we talked about in the class? SGD. What was the hypothesis space there? So think about it. I mean, each one of you has to know the answer to this. So we talked about gradient descent and then stochastic gradient descent. What was the space of function the gradient descent algorithm searched in? What did we learn? What was the output? Yes? All numeric vectors. Yeah, all vectors of dimensionality the same as the example. What does that mean? So all weight vectors W, which means what is the hypothesis space? If you take the vectors and you think about them as functions. So that one way to think about it, all vectors. But if you think about it as function, what is the function defined by this vector? You take the vector, go ahead. All linear function. You take the vector, how do you compute the value of the function? You take the vector, you dot product it with x, the example, right? That's a linear function by definition, right? So the space we worked with is the space of all linear functions. That's a continuous space because W, the weight vector, all vectors could be, each coordinate could be any real valued function, any real valued number. Okay? Everyone is with me on that? So this is just a simple case of conjunctions. In fact, I want to say one more thing about this conjunction. What's happening here? Okay. So we talked about various learning algorithms, a number of mistakes, and we gave this theoretical bound. What will this theoretical bound, by the way, be in the case of conjunctions? Remember, this is the conjunction we talked about last time, x2, x3, x4, s5, x100. You already know, because you've seen it in some of the quizzes, that the number of conjunctions over n variable is 3 to the n. Think about it again if you're not sure. I have n variables. When I build a conjunction in each place, first, second, third, up to 100, I can either put the variable, x7, or I can put the negation of the variable, not x7, or I cannot put anything. So I have 3 options for each slot. I have 100 slots. So it's 3 to the n. Log of this is n, which means that what we did before when we talked about this elimination algorithm that makes n mistakes is okay with this, right? So we make a logarithmic number of mistakes when the log of the size of the number of functions we deal with. Now notice that if I know already that I'm not just learning conjunctions, but rather I'm learning what I call here k conjunctions, I know that out of the 100 variables, only k are important, really. I don't know which k, but only k are important. Let's say just 10 are important, which is a more realistic case, right? So in many learning problems, you have a lot of features, but you know that most of them are unimportant. You just don't know which one. Well, think about the context-sensitive spelling problem that we talked about. I'd like to know whether to laugh or cry. I want to know whether type 1 or whether type 2. There's a huge number of features, but very few of them are actually relevant to the decision. You just don't know which ahead of time. Otherwise, you would write a few rules. So k conjunction is a realistic case. I'm telling you here that the number of k conjunctions is n choose k, 2 to the k. Think a little bit about it. N choose k is something like n to the k. Think about the 2. And therefore, log of that is k log n. Much, much smaller than n. Okay? So a very important question here is, can we actually learn with these many number of mistakes? You want to learn a function over n variables, but you want to learn it with logarithmic number of mistakes. So think about it. If you have 1,000 variables, the number of mistakes you're going to make is going to be order of 10. If you have 1,000,000 features, dimensionality of 1,000,000, the number of log 1,000,000 is 20. So order of 20 mistakes. Much, much better than 1,000,000 mistakes. So the question, can there be an efficient algorithm, or that efficient an algorithm? We actually are going to show in your problem set that this is possible, but more importantly now, this is still a finite hypothesis space. And I want to move to the infinite hypothesis space and ask, can we bound the number of mistakes there too? And intuitively, you may think, well, maybe not, because I can change each one of the coordinates in my weight vector W infinitely many ways. How could I bound the number of mistakes? And this is what we want to talk about now. So how do we move from this conjunction case, which I talked about because it's simple and you can see the learning algorithm, to this general case, which is this linear threshold function, where what we are learning is this weight vector W. So I want to remind you that we said, well, many functions are linear. Specifically, we talked about conjunction. So I'm reminding you here, this is a conjunction, x1 and x3 and x5, and we wrote it as a linear function. How did we write it as a linear function? We took the weight vector. Here I have weight vector of size 5. And we said, let's put weight 1 on the first, third, and fifth coordinates, the threshold 3. So the function y equal x1 and x3 and x5 is identical to the function this weight vector dot product with the x vector minus 3. Everyone agrees with that? So think about it. So really, what our elimination algorithm that we talked about last time really started with a weight vector that is all ones. All the variables are important. And whenever we made a mistake, we changed the wi from 1 to 0. This is equivalent to saying we eliminated this variable from consideration. We knew that it's not part of the conjunction. Okay? Can you see that the algorithm we did last time is basically this? Changing the wi's. Now, in general, when we want to learn real valued w's rather than just 0, 1 w's, we're going to change the wi in more carefully. Still, the representation is going to be this, which hopefully you agree it's the same as this, only that the w's are going to be different numbers. So maybe w2, instead of being 0, like it is here, will be 0.001, because we will never eliminate it completely. We'll just go down with it. So it's the same representation. This is the representation we want to move to, because why do we want to move from conjunctions to these linear threshold functions? What's wrong with conjunctions? Yeah?
They're absolute, because they don't take, nuance so much into account. It's either on or off. It's not something might be somewhat important, but not totally important.
It's more expressive, basically, right? So think about this linear threshold function can represent conjunctions, can represent disjunctions. You did it in the quiz. Can represent functions like m out of n. Can represent many, many, many functions, including conjunctions. So it's a lot more expressive. And we want to be more expressive. We want to have the ability to learn more functions. And in fact, there are also complexity theory reasons. Even if we wanted to learn conjunctions, it's actually better to learn it as linear threshold function, which is actually an interesting claim. So I'm not going to go into the details of this, but even if you were after a conjunction, it's actually NP hard to learn the best conjunction there is. Similarly, what we said in decision trees, even if you're after a decision tree, it's NPR to learn the best decision tree there is. So in this case, instead of learning conjunctions, we are going to learn linear threshold functions, and that's going to be efficient. So if the expressivity argument that I'm alluding to here isn't convincing for you, you can be convinced maybe by a complexity theoretic argument. It's actually going to be more efficient. Okay, so from now on, we forget about conjunctions, and we talk about general data sets, and we want to learn a linear function, which means we want to learn something like this. A W. What I'm showing here is W transpose X equals 0, because it goes through the origin. In general, we want to learn WX equal theta, the general setting. What do I mean when I say this? Again, you should know this. This is the vector W that you see here. This is the set of all points X. This is a good way to think about the set of all points X such that the dot product of them with W is 0. Okay? If you haven't thought about it this way, this would be a useful way. So we want to have an algorithm that learns this W. I'm reminding you of something that we already talked about, this canonical trick of hiding theta. I don't want to think about it as the sign of Wx minus theta. Instead, I'm replacing x by x with another coordinate, minus 1 in the n plus 1 place, and I'm replacing W with W concatenated with the theta in the n plus 1 place. And then, rather than saying Wx minus theta, I can say W prime dot product with X prime minus 0. So I basically shifted everything to the origin, and I no need to carry theta with me. So the pictures here, on the left side, you see something that goes through the origin. On the right side, I've added a dimension. And sorry, on the left side, you see something that does not go through the origin, Wx equal theta. On the right side, I added a dimension, but now my space goes through the origin. Okay. So with this, I can present a new learning algorithm that is going to learn this W. We already talked about what does it mean to learn this W, and with stochastic gradient descent, and we said that basically it's a search algorithm where we start with some W, we measure how well we are doing, and we correct. This is what Perceptron will also do, only that it's going to do it in an online, mistake-driven way. Perceptron is an algorithm that was invented in the 50s, at the same time by Rosenblatt and by some Russian mathematicians. Rosenblatt was really a neuroscientist, and the way he thought about it is that the way he wrote it is when a target output value is provided for a single neuron with fixed input, it can incrementally change weights and learn to produce the output using the perceptron learning algorithm. So this is what he had in mind. He had this linear unit, neuron, where xi's are the inputs, wi's are the weights on the exons, if you want, and then there's a linear sum, and potentially a gate, some nonlinear gate that produces the output. That was his perspective. Now, perceptron has become, in some communities, synonyms to linear threshold unit, just this unit that takes input x1 up to xin and multiply them by a weight vector. I typically use perceptron as the algorithm, not the linear threshold unit, because you can learn linear threshold units representation with other algorithms, as you will see. Okay, so that's what we do. So we have a function that maps x to plus or minus 1. We represent it as the sign of dot product WTX. You can think about x either as Boolean or as real-valued x's. W always now is going to be real-valued vector. Given a collection of examples, x1, y1, with the label x2, y2, xm, ym, that's what we're going to do. We're going to initialize the W to 0, for example. We're going to cycle through all the examples. In real life, you're going to do this many times, not only one through the m examples. And we're going to do this online. That is, we predict the label of the instance x to be y prime, the dot product, the sign of the dot product. If I made a mistake, I'm going to change the weight vectors. If I did not make a mistake, I will not change the weight vector. So that's why we call it a mistake-driven algorithm. You only change if you made a mistake. If I did make a mistake, how do I change it? This way. So W, the new W, is going to be the old W plus some learning rate here, R. Think about it as 1 for now, times Y times X. So what does that mean? So Y can be plus or minus 1. So let's assume that the example is positive, and I thought that it was negative. So y is plus 1. The example is positive, so I'm going to add x to w. If the example is negative, y is minus 1, I made a mistake. I thought it's positive. I'm going to subtract x from w. Okay, so it's a very simple algorithm. You take your w, you either add x to it or subtract x from it. Notice that the way we think about it here is w and x. X is my example, w is what I'm learning, my weight vector. They all reside in the same space. This is actually a conceptual thing that is important to remember because we'll use it. So here is what happens. So I have a bunch of examples here. Red are positive example, blue are negative example. What you see here is x, y equal plus 1 for red. Wx t equals 0 is this line. This is w, right? So w is always perpendicular to the decision surface, the decision hyperplane in this case. And the arrow points in the direction of the positive examples. So you can see that I'm going to make a mistake on this example on which I want to predict on, this red example, right? Because it's a positive example, but my arrow points to the other direction. So what do I want to do? I want to add this x, the vector. I want to add this vector to the w. So this is, I show you here what happens to it when I add x to the w. And my new w is going to be this. Okay? Again, so this is my new w. This is my new wx equals 0, perpendicular to this w. I have a new hypothesis, and I'm going to continue making predictions. So let's choose another example. So now I'm going to choose this example. Again, it's a positive example, but you can see that I'm going to make a mistake on it because the arrow points in the other direction. So it's on the wrong side of the hyperplane. And again, I'm going to add this x to w. I'm showing you x here, and x when it's added to w. And this is going to be my new hypothesis space now. Right? This is previous w plus the x on which I made a mistake. Now you can see that I'm not going to make mistakes anymore on this data set. Agreed? All the red points are on the right side. All the blue points are on the other side. No more mistakes. Which means I will not change my hyperplane anymore on this data set. Okay? So one question you want to ask yourself, is this just a dream and I made 2 mistakes and stopped? Or is this something that will happen in general, that at some point we're going to stop making mistakes? Yes?
What is R in this?
Oh, so the learning rate? So here R is 1. And the reason it's, the way you can see it's 1 is that, let's go to the, okay, so just a second. So you can see in the middle figure, x as a vector, the top one, the top arrow. This one, this is x, and this is x when I'm adding it to w. If r was 2, then this would have been x, and this would have been twice as long, because I would add 2x to w. So here I use just r as 1. Other questions? Yeah.
What is it that changes the slope of the hyperplane?
The fact that I'm changing w changes the slope. Right? So I'm not just multiplying w by 2, which will not change the slope, just increase the size of the numbers. I'm actually adding something. So let's assume w is 1, 1, 0, 0, 0, 0, 0. I'm adding 1, 0, 0, 0 to everything. I change the slope, right? Because I changed one of the, just w1, didn't touch the others. This is changing the slope. Yeah?
At each iteration of an algorithm, how does it choose which data point to look at?
You present it to it. It's just like stochastic gradient descent. Choose a random example, say, or someone presents it a random example. So why are you asking? So the intuition might be, maybe the order is going to matter. Right? So maybe what I learn depends on the order in which the examples are presented to me, which could be a good intuition. And in real life, definitely could happen. So first of all, what we're going to do, we're going to cycle through the data many times. Second of all, I'm going to show in a few seconds that in principle, it's not going to matter. The overall performance of the algorithm will not depend on the order of the examples. In practice, it will matter unless I'm cycling many times. Yes?
Can you also add all those points and then change that way, or you have to go point by point?
So that's the data I was given.
No, but like, if you look at that, you have like 3 points, 3 red points that you can point at and change that way, right? And can you just add the position of those and then change that way, like find the average?
Will that be the same algorithm? So how did you choose the examples that you want to add?
In that case, you said the direction is wrong, right? The error is wrong, so you chose that red top, bottom, and then change the direction of that leads in that direction.
Yeah.
Change the slope. But then there's only one example that has the wrong direction. It's like 3 of them, right? 3 on the top.
No, all 3 reds at the top are mistakes at this point.
So you choose one of them to change the direction.
Yes.
How about I choose all 3 of them?
Yeah, so that would be another algorithm. So basically what you're saying, take a few positive examples and use them as one example. Make a new example from them. The thing is that you knew already that these 3 examples are going to be mistaken prediction. In order to do this, you have to evaluate your hypothesis on all these examples. So if you are doing that, and then averaging, yeah, you're wasting your time. Okay, so that's the algorithm. And just writing it here again, and I want to make a couple of points. So first of all, think about the case where x is Boolean. X is 0 and 1. What happens then when I add ryx to w? So again, we're thinking about r as 1. So I'm either adding x or subtracting x from w. Think about the case where x is 0s and 1s in terms of efficiency. What's going to happen? Let's assume that you have million dimensions. X is a million dimension. So in the standard case, you will have to make million additions. Right? Every dimension of wi, you'll have to add the appropriate dimension of xi. Agreed? If it's 0s and 1s, what will happen? Yeah?
So I guess you just, I don't know if this would also be linear or faster than linear, but you would just find all indices where x is feature space where x is 1, and then you just increment each area.
Right, so if x is very sparse, that is out of the million, only 100 are 1s, you only need to do 100 additions, right? Now, of course, this has to come, as you say, with a good representation of the data. Because if you have to go over all the million indices and search which are 1s, you did nothing. But if you represent it in such a way that you have a list of all the 1s, then the list is going to be of size 100, and updating the W is going to be much faster. You will not have to touch a million dimension, you'll have to touch 100. So sometimes this is really important because in a lot of cases, the data is sparse. That is, very few of the features are on. Most of them are off, so you want to represent it this way. A second comment that I want to make is that we always talk about it in terms of whether the dot product Wx is positive or negative. Equivalently, I can look at this more complex function that I've written here on the right, 1 over 1 plus e to the minus wx, 1 over 1 plus e to the minus dot product, and I'm going to ask whether this is greater than a half or less than a half. You should convince yourself that these two are the same. If you need help, this is the graph of e to the x, and you can see that e to the x, when x is 0, it's 1. Therefore, when wx is 0, what you get there is exactly a half. Right? If it's less than that, it's greater than a half. It's more than that, it's more than a half. So these two functions are equivalent. You would think that the one on the left is much simpler, but as we will see, we'll hint about it today and we'll justify it a little bit later, this can be thought about as the probability that y is positive given x. So one can give a probabilistic interpretation to this, and therefore the decision that we are making when we say wx is positive or negative, really, it's equivalent to saying, under some assumptions, the probability that this example is going to be positive is greater than a half, so I'm going to say plus. I'm going to say 1. Okay? Okay, so a few historical comments that are important. So clearly we learn, Perceptron learns linear functions. Obviously, we can learn linearly separable functions. If you have a more complex function, you know, the examples are in the space in such a way that there is no linear function separating them, you cannot learn it with Perceptron. And this was actually known to Rosenblatt when he wrote the algorithm. And he himself asked what pattern recognition is the old name of machine learning, but this is in his book from '59, what pattern recognition problems can be transformed so as to become linearly separable. So he actually had in mind these pictures that I showed you earlier in the semester of blowing up the feature space so that things that are not linearly separable will move to be linearly separable. Nevertheless, in '69, Minsky, that you probably heard about, the famous guy, Papper, that you also probably heard about, wrote a very influential book. It's called Perceptron, that shows that Perceptron cannot represent linear functions. The book is, by the way, still worthwhile reading. There is a new edition, well, new from the time I was a PhD student, so sometime in the 90s. The old book came with handwritten notes of Minsky. So you can find it and you'll see his handwritten note on the old book. They showed really that there are many functions that cannot be that are not linearly separable. They showed, for example, that in vision, if you take patterns and represent them using local features, which makes sense, you cannot represent different properties of images like connectivity, symmetry, and so on. And therefore, they said, Perceptron are bad. Let's look at other approaches to learning. This actually stopped research on neural network for about 20 years. So in the 50s or early 60s was the first wave of neural networks. At that time, it was neural network of depth 1, Perceptron, died because of the book of Minsky and Papert, came back in the early 80s, died again in the mid-90s. It's coming back again if you read the news. So it's really the third wave of this. So interesting to know that, you know, some books can be influential on this. Okay, so what do we know? In fact, this was already known to Rosenblatt. he said, hand-wavingly, that if there is a set of weights that are consistent with the data, another way of saying, if the data is linearly separable, so you plot these red points and blue points in such a way that there is a hyperplane separating them, Perceptron will find them. He knew that. He didn't know how long it's going to take to converge. He also knew that if the training data is not linearly separable, then Perceptron will not converge and will basically cycle between multiple hypotheses and will never stop because it will never find a good stopping point. Again, in more sort of recent terms, we can talk about it when we stop it, how good is it, right? So we're going to stop it at some point. Will it be so bad or will it actually be good even though it's not perfect? So is it robust? So we are going to answer these questions. In fact, the answers were known already then, as you will see. I'm just rewriting Perceptron in a slightly different way here, because you're going to see it if you look at other places in different ways. The reason I'm writing it again in a different way here is just to make sure that you know that even though we're talking about it as Wx equals 0 or greater than 0, less than 0, this is because we did this canonical mapping. Really, you are updating the W, but you're also updating the theta, right? Only that after the canonical mapping, the theta behaves like W with index n+1, so you don't feel it. Here I've written it more explicitly so you can see that for every xi, if y hat is my prediction, right, the sign of the dot product, this is the notation for the dot product, wx minus theta, when I make a mistake, I'm updating w by adding the learning rate times y times x, and I'm also updating theta in exactly the same way. Okay? So this is just in the same algorithm, just I'm explicitly updating w and theta. Okay, what do we know? So this is a theorem, again, from the 60s that shows that we completely understand Perceptron. And it's actually a very, very interesting algorithm. So I'm going to state this formally. I'm not going to prove it, but we'll at least discuss what it means. So Perceptron maintains a weight vector. I'm going to initialize it, W0 to be all zeros. When we get an example x, we predict according to the linear threshold function. That is W dot product x, whether it's greater than 0 or not. And the theorem says this. Let's assume that I'm given data x1, y1 up to xt, yt. This is the set of examples, and I'm assuming here that xi are in Rn. I'm assuming here that all the xi's, all the examples, have size less than R. I didn't define size under the assumption that we all know what I'm talking about. We can think about size here. This is xi with these two lines on each side as L2 norm. So it's the sum of squares of the coordinates of x. And I'm assuming that this is less than R, some fixed number. Is this a big assumption? To assume that xi, for all I, the size of them is less than R. Yeah?
No, because you're assuming your data is practically finite, and you can just set R to be kind of flexible.
Yeah. So I have t examples in this case. So I'm taking the largest example, and I'm saying that's capital R. So I didn't make an assumption. It's just a notation. Okay? And I'm assuming that yi is plus or minus 1. These are my labels. I'm assuming that u is also a real valued function, and this is the truth. That is, this is the linear separator. separates the data. So basically, I'm assuming the data is linearly separable. And I'm also assuming that there exists some gamma, positive, such that when u is equal 1, again, notice that I can always assume that u is equal 1, because look at this here. If some of the points satisfy that u times x is positive, and some satisfy that u times x is negative, I can multiply everything by 7. Those that were positive will still be positive. Those that were negative will still be negative. So scaling the size of the separator is not a problem, right? So I can always assume that the true linear separator has size 1, okay, which I'm assuming here, u equal 1. And I'm also assuming that yi times u dot product x is greater than gamma for all I. So what does this mean? My gamma is going to be my complexity parameter. It will indicate how complex is the data, really, that I'm trying to learn. So what does this really mean? Is this a big assumption to assume that I have this gamma? The same kind of question that I asked about the R before. And really the same kind of answer, so someone else can give me the answer. Big assumption, not a big assumption. So before, you told me, well, you have T examples, measure the size of each of the example. Basically, the size means how far they are from 0, from the origin. So it's like putting a ball around all the examples. And take the farthest one and call this R. So I can always assume that all the examples have size less than R. Now I'm saying that for all I, this dot product is greater than gamma. Notice that what I'm really saying is that if it's a positive example, right? So if it's a positive example, then I want u dot product x to be positive, right? And y is also positive, so this is positive. If it's a negative example, what do I want the dot product u x to be? Negative. But y is also negative, so this is still positive. So this product y times the dot product is always going to be positive on correctly labeled examples, right? Again, if the example is negative, y dot product x is negative. Sorry, u dot product x is negative, but y is also negative, so the product is positive. And if x is a positive example, this dot product is positive, but y is also positive. So we should agree that all of this is always positive on my training data, but why can I say that it's always greater than gamma? Suggestion? If I were to ask you, yeah? Yeah, so I can write this term for all examples. I know that all of them are positive, and I'm going to choose the smallest one and call it gamma. So this gamma always exists. It really basically, it's some kind of show me how far these examples are from the linear separator. And then the claim is that the perceptron is going to make at most r square over gamma square mistakes on this example sequence. So let's first see what it says. So first of all, we said that the perceptron is going to stop making mistakes. which is kind of interesting because the perceptron learns an infinite large hypothesis space. All weight vectors could be in the output of the perceptron, all real valued weight vectors. Nevertheless, I said that it's going to stop making mistakes. And see what are the complexity parameters here. So the number of mistakes is going to grow with R squared, which is the size of the examples. If I have big examples, it's going to take more time to stop making mistakes. And it's inversely proportional to gamma squared. And gamma, you can think about the distance of the examples from the line. And again, think about it. If the examples are very close to the line, to the true line, it's going to take our algorithm a lot of time to fit between the positive and negative. If, on the other hand, all the positives are here and all the negatives are there, it's going to be relatively easy to find something that separates them, right? So it makes sense that the number of mistakes I'm going to make mistakes until I find something that separates the data. The number of mistakes I'll make is going to be inversely proportional to this gap, to how far the examples are from the linear function. Make sense? Questions? Okay, so this is really a magical thing in some sense. How do you want to understand it? You want to understand it in the following way. So there is a proof here. I'm not going to give the proof. If you won't go over it, it's actually cool that it's a one-slide proof, a little bit of algebra, not too complicated. But the key thing to understand is that this means that if the data is linearly separable, now it's not only this data, right? I only saw T examples, but maybe you'll give me in the future additional examples. Will I make mistakes on them or not? This theorem says, if all the examples that you'll ever see satisfy these conditions, that is, they are separable. How separable they are? Gamma separable. So all the positive example and the negative example satisfy yi times the dot product u with x is greater than gamma, you will stop making mistakes after these many mistakes. It doesn't matter whether you've seen all the data or you haven't seen. As long as the data is separable this way, you're okay. Okay? Questions? Okay, so something to think about here. A couple of comments. One is that the dimensionality of the examples and of W did not come in here. All we care about here is this gamma, this separating thing, which is a little bit surprising, I think. We will see that actually these are related a little bit when we'll talk about examples. Another thing is that it's really important to understand that for us, X and W lie in the same place. Examples and the weight vector, what we learn, the hypotheses, are in the same space. That's going to be important. We'll see it coming back. And as I said, the interpretation of the theorem is also important. So it's not a statement about training. It's a statement about all the examples that you'll ever see, as long as they satisfy this separability condition. Questions? Yeah?
Can you just explain again, please, where we're getting gamma from?
So basically, I'm saying, I'm assuming that the data is linearly separable. That is, there exists a U such that dot product Ux times Yi is always positive. That's another way of saying the data is linearly separable. Everyone should be clear about this. Again, I'm saying it. Another way of saying the data is linearly separable is to say that the dot product ux times y is positive. Moreover, because I gave you a finite set of examples, I can look at this minimum size of this product and call it gamma. So now, all these examples satisfy this gamma. And I'm claiming that this gamma, which kind of says how far am I from the truth, the true linear separator, we're going to call this margin. It's going to be related to the margin of the data, the margin between the positive and the negative, if you want. This margin really determines how difficult the problem is. If it's really small, problem is difficult because it's hard to fit the linear separator. If it's really big, problem is easier. And therefore, the number of mistakes, it makes sense that it's inversely proportional to it. Okay. Other questions? Okay, so one thing we want to talk about is robustness. So what happens if we are in the non-separable case? In the non-separable case, I want to think about the extent to which a data point fails to be gamma away in the right side, right? So this is the truth here, this thick line here. This is my gamma separator, right? My thickness gamma. If all the red points are here and all the purple points are here, the data is linearly separable, okay? If some of them go into this gamma margin or even move to the other side, then it's not linearly separable, and I want to measure the extent to which this is happening. So we can measure it with this, what we call a slack variable, psi I. Psi I is the maximum between 0 and gamma minus this product that we talked about before. Now think about it. So if the point is exactly on this dashed line, it means that yi times wx is exactly gamma. Okay? So if I'm on the right side, it means that yi wx is greater than gamma, which means the value of this is 0. Okay? If I'm inside these dashed lines, or I even move to the other side, then gamma is going to be greater than this, and therefore there's going to be some number, and it's going to grow linearly with this dot product. Okay? So psi is 0 when I have a good margin. I'm outside these dashed lines. Otherwise, I'm suffering, and I'm suffering linearly with this dot product. So I'm going to denote this square, the sum over this psi I, square of psi I, over all my examples, square root of it. So basically, it's L2 of my slack variables. And a new theorem would say that the perceptron is guaranteed to make no more than these many mistakes on any sequence of examples in general. So even if the data is not linearly separable, as a function of gamma and of this slack variable, D2, I can tell you how many mistakes we're going to make. So we are going to make mistakes, but we can bound the number of mistakes as a function of the extent to which we are not linearly separable. So basically, this tells us, well, perceptron is going to be robust to noise. It's not going to stop. You'll have to stop it at some point, because otherwise you will always make mistakes and you'll change the hypothesis. But once you decide to stop it, you can measure the quality of the perceptron as a function of this slack variable. Okay, so a couple other things that I want to say before we are done here. So one is, if you think about Boolean functions or even conjunctions, again, you can actually think about perceptron and show that perceptron is actually going to make order n mistakes on conjunction. It doesn't matter whether it's k conjunction, that is, the conjunction depends only on a small number of variables, or it depends on all of them, or almost all of them. It's going to make order n mistakes. Recall that we said at the beginning today that the halving algorithm suggests that we can do better. Logarithmic in n, perceptron is not achieving that. This can be achieved by another algorithm that you will play with in the homework. A couple other practical issues that I wanted to say. So I already said before, there are many, many extensions to perceptron. We're going to talk about them, I guess, on Wednesday. In fact, I'm going to stop here because we'll talk about the extension on Wednesday. Final questions on this? Okay. See you Wednesday then.
I have a small question about homework 1. Is it fine if I can ask it to you?
Yeah, you should have asked in class, actually, because I'm sure other people have the same question.
Yeah, I didn't think about it. I have a bit of confusion of differentiating a feature and a feature type.
Okay.
So in the example you give for the features was the 390. So is that one feature type, or is that 390 different feature types?
So these are 390 features.
Okay, so but it's one feature type.
You can say that, yeah.
Okay.
Because they're all decision trees, yeah.
Okay, and so do we need 15 different? The questions ask for 15 feature types, right? We have to create.
No, we gave you the feature types at the beginning. Sorry. You're talking about the 390? So the 390 are features,
okay.
But the feature types we gave you were something about first character is something, okay. So that's a feature type, right? Okay. It has 26 values.
Okay.
26 features are generated from this type.
Okay, and this
second position again, and so on. So there are 15 like this times 26, okay. Probably give 390.
And do we need to add more, or is this fine for the homework?
That's the minimum.
Okay,
I mean, you could, if you want to try, add more, but you definitely have to use these 15 types.
Okay, yeah. Thanks very much.
Sure.
I also have some thoughts about the homework too. So it seems like we are using the results from those 200 decision trees as features.
Yes.
But the SGD trained on this is something like the weights in this SGD is a measure of how trustful each decision trees are.
Yes.
Something like this is
something like this, yeah. Although it's not individual trust because you train it globally on all the features together, but yeah, you can think about it.
Okay, so
it's the weight it assigns to
each decision tree.
Yes.
Are this one trustful? Is this one making the correct decision? Something like that.
Something like this, but not exactly, as I said, because you're not checking each tree independently.
Mm-hmm.
Yeah, but you're right. I mean, eventually the weights, if you look at the vector of the 200 weights, you can say, this is a good tree, this is a bad tree, okay, based on the size of the weight.
So is this approach commonly applied in real-world projects?
Yeah.
So they're actually using another approach of...
Right, I comment on it in class. This is perhaps, this is one of the most important learning algorithms there is.
Okay.
to use decision trees
To
as
generalize,
stumps.
yeah, it's something like to generalize the regional features to make it more.
You build a very expressive features this way, but each feature by itself is not powerful enough as a classifier, so you put them together into a linear system. Now there are other ways that we will see to, one, learn the features, two, give them weights. But in principle, this is a very important scheme.
Okay, thanks.
Sure.
I have a question. So, perceptually, like I'm trying to think about the whole thing, the stumps. Like I'm having difficulty understanding why this is useful. Like
Why the stumps?
yeah, why is that when you're making the stumps, you train, so you do randomly choose half of the data, and then you train the decision tree, and then you predict with the same data. So like you have, let's say 200 decision trees, and then you predict with the same data. What do we use the same data? Like I don't know, it just feels.
So basically, the data that you have is the data that you have. That's it, right?
Yeah, because like when we are doing like testing on like SGD, all of that, you use a different data, like 5 folds. You use a different data to predict. In this case, you're predicting the same data that you use to make the decision tree.
Yeah. But you see, the training data that you have is all you have, right? There's nothing else. I can either extract features directly from each example. This is what you do when you do decision trees. Or I can say, you know what, I want more expressive features. Features that represent a bunch of the data together. So I'm learning decision trees on half the data. And I want to, and my new features are going to be this. So now I take every example and I convert it to a new example. Right?
So the part that you have to do predict for the same stumps algorithm, you have to, when the X is inputted, you have to change the X to the new feature space.
Well, first of all, I take the X, and I run it on 200 trees.
Yeah, and then
I got a new vector. So for every X, I got 200 numbers. I treat them as my new example. Right? Think about it, it's a conversion of X1 to a 200-dimensional X prime. Now I take X2. I run it through my 200 trees. I got another representation of this example.
So it will be
and I do this, whatever, 500 times for each
if you have
example.
700 examples, it will be like 700 by 200.
Exactly.
If it's 700 examples.
Yes.
So my question is, for the decision tree, when you're predicting, at the beginning you're making a model. You're making the, I guess I don't know how, like when you do the prediction for the decision tree, after you do the half, after you have 200, you do the prediction of X. Why don't you use 5 folds in that part?
Yes.
To do it many times, like every single possible way, to have the best outcome there, instead of doing it and then do accuracy afterwards.
What would it give me that I do 5-fold? I mean, so I will have 5 different trees.
You would have, you would do
but,
like.
But what I want here, my goal here is slightly different. This is the data conversion.
Yeah, but I'm just trying to think, if you do a 5 folds, wouldn't you be able to get better features to then train on the SGD and then get the model?
Let's continue with this. What will I do once I do the 5-fold? So basically I trained 5 different trees.
Yeah. 5 different trees for every tree, so it's like 200.
What do I do now?
Then you input it, you do SGD with all those trees.
But which trees?
Okay.
I have to decide, right? I have to decide. So we just gave you one way to decide. Perhaps there are other ways. Perhaps you can take all of them, right? So you can say not only take half the data, but also run it 5 times on this half the data, where you subsample from this half. But statistically, it's not going to be much more robust.
Why
and you will have 1,000 instead of 200.
Is there a reason you chose half? Is there any specific reason?
You can do 80%.
It doesn't.
The thing is that it just shows you that there's so many ways, right? So if you choose half the data, there are so many ways to choose half the data that it's really random.
Yeah.
Well, think about it. 500 examples say, half the data is 500 choose 250. Huge number,
Yeah, it's a big,
right?
yeah.
So basically, just another way of saying choose random.
And then when I'm trying to change parameters for training, I know I can change it and do fivefold, see which one is the best one, but what is the range that I have to look for it? Because like the range is so variable. So like let's say learning rate. What is a good range for learning rate?
So in fact, scikit-learn is going to help you there because they have their own things. We're not going to tell you what to do. In the next homework, we're going to guide you a little bit on parameter search. But we just wanted you to play.
Yeah, because right now you have optimal for learning rate.
Yes.
But we don't know. I don't know. Like
you don't know
what the optimal.
Yeah.
Okay.
But scikit-learn itself searches.
Well, when it says optimal, there's no point for me to go search for a new. Isn't that already optimal?
No, I think you mean when you set optimal in scikit-learn. Yeah.
Is that, that seems like it's the best.
Well, frankly, I don't know exactly what they do. So I'm not sure if it's really optimal, but they call it optimal.
Okay, makes sense. All right, thanks.
Question about the bonus? Yes.
So like some people